At the European Space Agency's Operations Center in 2018, astrophysicist Amina Helmi sat before her computer screen, examining data that had traveled across 500 million miles of space. The Gaia spacecraft, positioned at a gravitationally stable point between Earth and the Sun, had been measuring the positions and velocities of stars with unprecedented precision. For months, Helmi and her team at the University of Groningen had been analyzing these measurements, looking for patterns in how stars moved through the Milky Way. What appeared on her screen that day should not have been possible. 30,000 stars scattered across the entire sky were moving wrong. Not slightly wrong, catastrophically wrong. Their orbits cut through the plane of the Milky Way's disk at steep angles, elongated trajectories that carried them from the innermost regions of our galaxy out to distances of 20,000 parsecs and back again. These weren't the orderly, roughly circular paths that most stars in our galaxy follow. When Helmi examined their chemical signatures using data from the Apogee ground survey, the evidence became overwhelming. These stars contain different ratios of elements than stars born in the Milky Way. Their metallic content told a story of formation in a different environment, under different conditions, in a different galaxy entirely. They were ghosts, the remnants of a galaxy that had been torn apart and consumed by our own. Helmi called it Gaia-Enceladus, after the giant in Greek mythology born of earth and sky. Approximately 10 billion years ago, when the universe was less than half its current age, this dwarf galaxy had collided with the Milky Way in a merger so catastrophic it had fundamentally reshaped our galaxy's structure. The stars Helmi identified were all that remained. 50 billion solar masses of stars, gas, and dark matter had been absorbed, digested, incorporated into the Milky Way's body. The debris now stretched across nearly the full sky above our heads. But this wasn't the first time our galaxy had eaten another. To understand how galaxies consume each other, we need to step back to the earliest moments after the Big Bang. Matter distributed itself in an almost uniform haze, with tiny variations in density that seem insignificant until you account for the passage of time and the relentless pull of gravity. Regions that were even slightly denser than their surroundings began pulling in more matter. Those regions grew denser still. Gravity is patient. It compounds. The Lambda CDM model, our current best description of how cosmic structure forms, describes a hierarchical process. Small things form first. Pockets of dark matter a few million times the mass of our sun collapsed into halos, and within these halos, the first stars ignited roughly 400 million years after the Big Bang. These proto-galaxies were nothing like the grand spiral we inhabit today. They were small, irregular collections of a few million stars, bound together by dark matter scaffolding we still cannot see directly. But they were the seeds. Here is where the hierarchy becomes violence. These small galaxies didn't evolve in isolation. They moved through space, drawn by gravity's invisible threads toward regions of higher density. When two galaxies encountered each other, several outcomes became possible. If they passed at high speed with significant separation, they might gravitationally perturb each other and continue on. If they approached more slowly, at closer range, they might enter into a gravitational dance that could last billions of years. And if the conditions aligned, they would merge. Astronomers distinguish between several types of merger based on the mass ratio between the colliding galaxies. When two galaxies of roughly comparable size meet, we call it a major merger. These are spectacular collisions that can transform two spiral galaxies into a single elliptical one, compressing gas clouds and triggering starbursts where millions of new suns ignite within a few million years. When the mass ratio becomes more lopsided, when one galaxy is several times larger than the other, we call it a minor merger. And when the difference becomes extreme, when a giant galaxy encounters a dwarf barely 1/10 or 1/20th its mass, we use a different term altogether. We call it galactic cannibalism. Current observations suggest that between 5 and 25% of all galaxies are currently involved in some form of merger. This percentage might seem low until you consider the timescales involved. A typical merger between two galaxies unfolds over hundreds of millions to billions of years. From our perspective, frozen in our brief human moment, it appears as a static tableau. But compress those billions of years into a few minutes, and you would see galaxies as living things, writhing and consuming and being consumed, growing through incorporation. The process raises a fundamental question that astronomers still debate. Most large galaxies, including our own, harbor supermassive black holes at their centers. The Milky Way's black hole, Sagittarius A star, contains roughly 4 million times the mass of our Sun, compressed into a region smaller than Mercury's orbit. These cosmic monsters exist at the hearts of nearly every galaxy we've observed. But which came first? Did galaxies form first, their gas and stars gradually feeding central black holes until they grew to millions or billions of solar masses? Or did the supermassive black holes form first, perhaps from the direct collapse of massive gas clouds in the early universe, with galaxies subsequently assembling around them like cities growing around crossroads? The hierarchical model suggests both processes happened simultaneously, feeding each other. Small black holes formed in the first proto-galaxies. When those galaxies merged, their black holes eventually merged too, creating larger black holes in larger galaxies. The process repeated, compounding over billions of years, building both the galaxies and their central engines through the same cycles of collision and cannibalism. Computer simulations, following this process from the early universe to today, can reproduce the distribution of galaxy sizes and black hole masses we actually observe. The math works. The universe builds big things by having small things eat each other. But here's what makes galactic cannibalism so different from our terrestrial metaphors. When galaxies collide, their stars almost never actually hit each other. A galaxy is mostly empty space. If you could shrink the sun to the size of a golf ball, the nearest star would be over 800 miles away. On galactic scales, stars are sparse motes drifting through vast darkness. When the Milky Way and Andromeda eventually collide 4.5 billion years from now, the probability of our Sun physically striking another star approaches zero. The stars will pass through each other like two clouds of gnats, interpenetrating. What does collide is gas. The interstellar medium, those diffuse clouds of hydrogen and helium drifting between stars, cannot pass through each other. When two galaxies merge, their gas clouds slam together at velocities of hundreds of kilometers per second. These collisions create shock waves that compress the gas, and compressed gas becomes dense enough for gravity to take hold. Dense clouds fragment and collapse. Protostars ignite. A merger between gas-rich galaxies can trigger star formation at rates 100 times higher than normal, converting millions of solar masses of gas into stars every year. Astronomers call these starburst galaxies, and they represent some of the most violent episodes of creation in the universe. Yet even this violence serves construction. The stars formed in these merger-driven starbursts will outlive the collision itself, becoming part of the merged galaxy's population. Nothing is truly destroyed. Everything is transformed, recycled, incorporated. We are made of atoms, forged in stars, that formed in galaxies that grew through cannibalism. Violence becomes us. You don't need telescopes or spacecraft to witness galactic cannibalism. You just need to be in the southern hemisphere on a clear night, away from city lights, looking up. There, spanning several degrees of sky, you'll see two luminous patches that appear to have been torn from the Milky Way itself. Early observers thought they were detached pieces of our galaxy's cloudy band, fragments of the great river of light that arcs overhead. They're not. They're separate galaxies, each containing billions of stars, caught in our gravity and slowly being torn apart. Ferdinand Magellan's crew documented them during the first circumnavigation of the globe in 1519. They already had names in indigenous cultures that had watched them for millennia. The Large Magellanic Cloud and the Small Magellanic Cloud became their European designation, named for the Portuguese explorer whose journey brought them into Western awareness. For centuries, they remained curious objects, their true nature unclear. Were they nebulae within our own galaxy? Distant star clusters? It wasn't until the early 20th century, when Henrietta Leavitt used Cepheid variable stars to measure cosmic distances, that astronomers realized these clouds were galaxies in their own right, separated from us by enormous gulfs of space. The Large Magellanic Cloud lies approximately 163,000 light-years from Earth. At that distance, it spans roughly 32,000 light-years across, making it a respectably sized dwarf galaxy. It contains somewhere around 30 billion stars, about 1/100th the mass of the Milky Way, arranged in a disrupted, barred spiral pattern. If you could see it from a distance, suspended in intergalactic space, you'd notice immediately that something is wrong with its structure. One side blazes with star formation, while the other appears quiescent. Its spiral arms are asymmetric, lopsided, torn. The central bar that once helped define its shape now sits geometrically off-center, twisted by forces that have been pulling at it for billions of years. The Small Magellanic Cloud, lying about 200,000 light-years away, appears even more disrupted. Astronomers long classified both Magellanic Clouds as irregular dwarf galaxies because their shapes defied easy categorization. Recent observations suggest they too once had barred spiral structures, but those structures have been mangled almost beyond recognition. The Small Magellanic Cloud contains perhaps 7 billion stars, making it roughly a quarter the mass of its larger companion. It appears to be not just one object, but possibly several clumps of stars loosely bound together, a galaxy in the process of coming apart. For decades, astronomers assumed the Magellanic Clouds had been orbiting the Milky Way for most of cosmic history. Faithful satellites bound to us by gravity, slowly spiraling inward over billions of years. Then, in 2006, measurements from the Hubble Space Telescope revealed something unexpected. The clouds were moving too fast. Their velocities through space suggested they might not be in bound orbits at all. Instead, they could be on their first passage through the Milky Way's gravitational sphere of influence, falling toward us from intergalactic space, their fate not yet sealed. This revelation transformed their story. Rather than ancient companions that have always been with us, the Magellanic Clouds might be recent arrivals, dwarf galaxies that formed independently and are only now encountering our galaxy for the first time. If they're in orbit, that orbit takes at least 4 billion years to complete. We might be witnessing their first or second close approach, the opening act of a gravitational tragedy that will play out over billions of years to come. Or they might have enough velocity to escape after this passage, fleeing back into intergalactic space, their brief encounter with the Milky Way leaving permanent scars on both parties. What makes them remarkable? What makes them crucial to understanding galactic cannibalism is that we can watch it happening. The Magellanic Clouds are close enough that we can measure their structures in exquisite detail, map their stars individually, trace the gas being pulled from them by our galaxy's tidal forces. Connecting them is a bridge of neutral hydrogen gas, an arc of material stretching across the 70,000 light-years of space between the two clouds. This bridge formed through tidal interactions as they pass near each other, their mutual gravity pulling gas from each galaxy toward their shared center of mass. But there's more. Trailing behind both clouds as they move through space is an enormous streamer of hydrogen called the Magellanic Stream. This structure extends more than 600,000 light-years across the sky, wrapping halfway around the Milky Way. It's a trail of debris, material ripped from the clouds by our galaxy's tidal forces. As they move through our gravitational field, The differential pull of gravity across their bodies literally tears gas out of them and flings it into intergalactic space. This process, called tidal stripping, is one of the primary mechanisms of galactic cannibalism. It happens through gravity's patient violence, applied over millions and billions of years. Recent studies using radio telescopes have revealed even more structure in this system. Leading the clouds in their motion through space is another streamer of gas, called the leading arm. Material torn from the clouds doesn't just trail behind them, it's pulled forward too, scattered in both directions along their orbital path. The Magellanic system is disintegrating in real time, and we are the force disintegrating it. What makes the clouds astonishing is that despite this ongoing tidal disruption, they remain vibrant, star-forming galaxies. The Large Magellanic Cloud contains the Tarantula Nebula, the most active star-forming region in the entire local group of galaxies. This nebula alone contains roughly 1 million solar masses of gas and spans 550 light-years across. It blazes with the light of newly formed massive stars, including R136A1, one of the most massive stars ever discovered. When first measured in 2010, astronomers calculated its mass at approximately 265 times the Sun's mass. More recent observations, with the Hubble Space Telescope, have refined this upward to around 290 solar masses, though the star has been losing mass throughout its life through powerful stellar winds. The tidal forces tearing the clouds apart are simultaneously compressing their gas, triggering new generations of star formation. They're being destroyed and reborn simultaneously. At the heart of the Large Magellanic Cloud, astronomers recently discovered strong evidence for a supermassive black hole containing approximately 630,000 solar masses. This discovery was announced in March 2025, making it the second closest supermassive black hole to Earth after our own Sagittarius A star. The black hole's gravity has ejected at least 21 hypervelocity stars that have been found scattered through the Milky Way's halo, stars moving so fast they'll eventually escape our galaxy entirely. Even as the cloud itself falls toward us, it's launching stars into intergalactic space at velocities exceeding 600 kilometers per second. The fate of the Magellanic Clouds remains uncertain. If their velocities are low enough, if their orbits are indeed bound to the Milky Way, they will eventually be completely consumed. Their stars will be scattered into our halo. Their gas will be stripped away or funneled toward our galactic center, where it might fuel new star formation or feed our central black hole. Their dark matter halos will merge with ours. In a few billion years, there will be no separate Magellanic Clouds, only their remnants distributed throughout a slightly larger Milky Way. Or, if they're moving fast enough, they might escape after this passage, flee back to intergalactic space as shredded, gas-poor remnants of their former selves, doomed to drift alone until some other galaxy captures them. But for now, on this night, under dark southern hemisphere skies, you can see them with your naked eyes, two patches of light, looking like fragments of the Milky Way torn loose and drifting. They're not fragments. They're entire galaxies dying in slow motion, and we are killing them. Gravity doesn't pull uniformly. This fact, simple and fundamental, drives galactic cannibalism. When the moon orbits Earth, its gravity pulls harder on the side of our planet facing it than on the opposite side. This differential creates tidal forces that lift our oceans into bulges on both the near and far sides. We experience this as the tides, the regular rising and falling of sea level as Earth rotates through these gravitational gradients. The moon doesn't have to touch Earth to move our oceans. It does it from 240,000 miles away through nothing but gravity's patient manipulation of space itself. Now scale this process up by factors of billions. A dwarf galaxy approaching the Milky Way experiences the same effect, but instead of water sloshing back and forth, it's stars being pulled from their orbits. The stars on the side of the dwarf galaxy nearest the Milky Way feel stronger gravitational attraction toward our galaxy than the stars on the far side. This differential force stretches the dwarf galaxy, pulling it into an elongated ellipsoidal shape. As it continues to approach, the tidal forces intensify. Eventually, they exceed the dwarf galaxy's own self-gravity, the force holding it together as a coherent object. At that point, it begins to come apart. The outer stars get pulled away first. They're farthest from the dwarf galaxy's center, most weakly bound, most susceptible to external forces. They get tugged out of their orbits and begin following their own trajectories through space. Trajectories determined more by the Milky Way's gravity than by their former home galaxies. As the dwarf galaxy continues its passage, more and more stars get stripped away in this fashion. The galaxy unravels like a piece of cosmic yarn. These stripped stars don't scatter randomly into space. They follow specific paths determined by the dwarf galaxy's orbit and the timing of their ejection. Stars pulled from the leading edge of the dwarf galaxy form what's called a leading tidal stream, a coherent structure of stars ahead of the galaxy in its orbit. Stars pulled from the trailing edge form a trailing tidal stream behind it. These streams can extend for hundreds of thousands of light years, wrapping around the host galaxy multiple times as they precess through space over millions of years. The Sagittarius dwarf spheroidal galaxy provides the most dramatic example of this process in action. Discovered in 1994, it lies on the opposite side of the Milky Way's center from us, currently about 70,000 light-years from the galactic core. But calling it a galaxy almost seems too generous at this point. It's more accurate to describe it as what's left of a galaxy. Computer simulations and observational evidence suggest it has passed through the Milky Way's disk at least 3 times, possibly more, over the past few billion years. Each passage strips away more of its structure. Today, the Sagittarius dwarf is surrounded by enormous tidal streams that wrap entirely around the Milky Way. These streams contain far more mass than the dwarf galaxy's remaining core. Astronomers have traced them looping above and below the galactic plane, crossing through our own position in space, extending for more than 1 million light-years in total length. We're literally inside the debris field of this dying galaxy. Some of the stars overhead, stars we count as members of the Milky Way's halo, were born in Sagittarius. They're immigrants, citizens of a realm that no longer exists as a coherent entity. The physics of this process involves several timescales working simultaneously. First is the orbital period, how long it takes the dwarf galaxy to complete one orbit around the Milky Way. For most dwarf galaxies, this ranges from a few 100 million to a few billion years. Second is the timescale for dynamical friction, a process where the dwarf galaxy's motion through the Milky Way's dark matter halo gradually saps its orbital energy. The dwarf galaxy acts like a boat moving through water, creating a wake in the dark matter distribution behind it. This wake exerts a gravitational pullback on the dwarf galaxy, slowing it down. Over multiple orbits, dynamical friction causes the dwarf galaxy to spiral gradually inward, bringing it deeper into the Milky Way's gravitational potential, where tidal forces become even stronger. Third is the tidal stripping timescale itself, how long it takes for tidal forces to actually remove stars from the dwarf galaxy. This depends on the dwarf galaxy's internal structure, its dark matter content, and how close its orbit takes it to the Milky Way's center. A dwarf galaxy on a highly elliptical orbit that passes close to the galactic center will be stripped much faster than one on a more circular orbit at larger distances. Near the Milky Way's center, the tidal forces become so extreme that a dwarf galaxy can be completely shredded in a single passage, torn apart in just a few tens of millions of years. Gas gets stripped even more efficiently than stars through a different process called ram pressure stripping. As a dwarf galaxy moves through the Milky Way's halo, it encounters diffuse gas, the hot ionized medium that fills the space between stars. This gas is thin by terrestrial standards, less dense than the best laboratory vacuums, but it exists. When the dwarf galaxy plows through it at velocities of hundreds of kilometers per second, it experiences a headwind. This ram pressure preferentially strips away the dwarf galaxy's own gas, the raw material for future star formation. The stars can hang on longer because they're discrete, self-gravitating objects, but the gas gets blown away like leaves in a hurricane. This explains a puzzling observation about the Milky Way's satellite galaxies. Of the roughly 60 dwarf galaxies we've identified orbiting our galaxy, most are essentially dead. They're called dwarf spheroidal galaxies, and they contain old stars, but no gas, no ongoing star formation, no nebulae or young blue giants. They're fossils. At some point in their history, something stripped away their gas and terminated their ability to form new stars. The leading explanation is environmental processes like ram pressure stripping and tidal stripping, gradual robbery committed by the Milky Way over billions of years. The Magellanic Clouds stand out precisely because they still retain gas and active star formation, but that's probably because they're recent arrivals who haven't experienced enough passages through our halo to be fully stripped yet. The dark matter in these systems complicates everything. Dwarf galaxies are dominated by dark matter, typically containing 10 to 100 times more dark matter mass than visible matter. This dark matter provides most of their gravitational binding, which helps them resist tidal disruption longer than they otherwise would. But dark matter also gets stripped. As stars are pulled from the outer regions of a dwarf galaxy, the dark matter in those regions goes with them. Computer simulations show that by the time a dwarf galaxy has lost most of its stars to tidal stripping, it has also lost most of its dark matter. What remains is a compact core where the density is high enough to resist further stripping. Some galaxies survive only as these cores strip down to their most tightly bound inner regions. Others get completely dissolved, their stars and dark matter entirely redistributed into the host galaxy's halo. The deciding factor is the dwarf galaxy's original mass and structure combined with the specific details of its orbit. Dense, massive dwarfs can survive multiple passages and remain identifiable for billions of years. Low-mass, diffuse dwarfs can be completely destroyed in a single close approach. Astronomers have a technical term for the radius at which tidal forces from the host galaxy start to dominate over a satellite's self-gravity. It's called the tidal radius, and for a dwarf galaxy orbiting the Milky Way, it typically lies somewhere between a few kiloparsecs and 20 kiloparsecs from the dwarf center. Material beyond this radius is vulnerable to being stripped on the next passage. Over time, as the dwarf loses mass and its self-gravity weakens, its tidal radius shrinks inward. The galaxy peels away from the outside like an onion losing its layers. The Canis Major dwarf galaxy, if it exists as a distinct entity, might be the closest example of this process to Earth. Discovered in 2003, it lies only about 25,000 light-years from the Sun, closer than the galactic center. It appears as an overdensity of stars in the direction of the constellation Canis Major, stretched out into a long filament wrapping partially around the Milky Way. Some astronomers argue it's not a real galaxy at all, but rather a perturbation in the Milky Way's disk caused by something else. Others maintain it's the remnant of a dwarf galaxy currently being shredded as it passes through our disk. The debate continues. Its very ambiguity illustrates how difficult it becomes to identify a galaxy once tidal stripping has progressed far enough. At what point does a galaxy cease to be a galaxy and become merely a stellar stream? When half its mass is gone? When 90% is gone? When all that remains is a chain of stars following a common orbit? The Virgo stellar stream provides a glimpse of the ultimate endpoint. Discovered through careful analysis of stellar motions, it appears as a coherent group of stars sharing similar velocities and chemical compositions scattered across a broad region of sky. Tracing their orbits backward in time, astronomers determined these stars once belonged to a dwarf galaxy that passed through the Milky Way's halo hundreds of millions of years ago. That galaxy no longer exists as a discrete object. The stream is all that remains, and even that will eventually disperse and phase mix until its stars become indistinguishable from the general halo population. In a few billion more years, there will be no evidence this galaxy ever existed, except in careful archaeological studies of stellar chemistry and dynamics. It will have achieved complete digestion. The stars remember. Even after their parent galaxy has been torn apart, even after billions of years drifting through intergalactic space, stars carry evidence of their origins encoded in their atmospheres. When a star forms, it incorporates whatever elements were present in the gas cloud that created it. That composition becomes essentially frozen into the star's structure. By studying a star's spectrum, the rainbow of light it emits, split into its component wavelengths, astronomers can identify which elements are present and in what proportions. This acts as a chemical fingerprint, a signature revealing where and when that star formed. Different galaxies have different chemical enrichment histories. A small dwarf galaxy that formed most of its stars early in cosmic history, then stopped forming new stars billions of years ago, will have a distinctive chemical signature. Its stars will be metal poor by astronomical standards, containing low abundances of elements heavier than helium, because there weren't many previous generations of stars to enrich the gas with metals. A larger galaxy with ongoing star formation over billions of years will show a progression, with older stars being metal poor and younger stars being progressively more metal rich, as successive generations of supernovae added more heavy elements to the interstellar medium. These chemical differences allow astronomers to identify stars that didn't originate in the Milky Way. When Amina Helmi analyzed the 10,000 stars with unusual orbits that Gaia had identified, she didn't just look at their motions. She combined the motion data with chemical abundances measured by the Apache Point Observatory Galactic Evolution Experiment, known as APOGE. This ground-based survey uses spectroscopy to measure detailed chemical compositions for hundreds of thousands of stars. When Helmi matched the Gaia data with APOGE's chemical data, the foreign stars stood out clearly. They occupied a distinct region in what's called the Hertzsprung-Russell diagram, a plot comparing stars' colors and brightnesses. They showed unusual ratios of magnesium to iron, ratios that didn't match the patterns seen in stars formed in the Milky Way. Their ages, estimated from their positions on the diagram and from radioactive dating techniques, clustered around 10 to 11 billion years. They all told the same story. They formed somewhere else, under different conditions, and were brought here by force. This forensic approach extends beyond individual stars to entire stellar streams. Each stream represents the debris from a specific dwarf galaxy, and the stars in that stream should share common properties. They should have similar chemical compositions reflecting their shared origin. They should have similar ages if the dwarf galaxy underwent star formation primarily during a specific epoch. And crucially, they should follow related orbits through space, their current trajectories linked by their common past. The Jhelum stream, named after a river in India, illustrates both the power and the complexity of this analysis. Discovered in recent surveys of the Milky Way's halo, it appears as a coherent group of stars stretching across a large region of sky. Initial studies tried to determine whether it originated from the Gaia-Enceladus merger or from some other dwarf galaxy. Using APOGE data, astronomers identified the brightest known red giant star in the stream and measured its detailed chemical composition. They also calculated its orbit backward in time using Gaia's precise measurements of its motion through space. The results suggested the Jhelum stream probably didn't come from Gaia-Enceladus. Its chemical signature didn't quite match. Its orbit differed from the typical orbits of Gaia-Enceladus debris. Instead, It seemed to represent a different merger event, possibly from a smaller dwarf galaxy or even a disrupted globular cluster. This conclusion illustrates an important point. The Milky Way's halo contains debris from many different accretion events, and disentangling them requires combining multiple types of data. Chemistry alone isn't enough. Orbits alone aren't enough. You need both, along with ages and spatial distributions, to build a coherent picture. At the Max Planck Institute for Astronomy in Heidelberg, astrophysicist Khyati Malhan led a project to create what they called the Global Dynamical Atlas of Milky Way Mergers. The goal was ambitious: to systematically catalog all the evidence of past merger events and assign specific stellar streams, globular clusters, and satellite galaxies to their parent dwarf galaxies. The project relied on a mathematical concept called action variables. Action variables are quantities derived from an object's motion that have a special property. They remain approximately constant even as the gravitational field changes. When a dwarf galaxy merges with the Milky Way, the orbits of its stars get perturbed and scrambled, but the action variables for those stars remain similar to each other and different from stars born in the Milky Way. This makes action variables powerful tools for identifying stars that share a common origin. Malhan's team calculated action variables for 170 globular clusters, 41 stellar streams, and 46 satellite galaxies using data from Gaia's third early data release. They then used statistical techniques to look for groupings in action variable space, clusters of objects with similar values suggesting they came from the same merger event. The analysis successfully identified 6 major merger events that have contributed to the Milky Way's current structure. The most significant was Gaia-Enceladus, also called the Gaia sausage, because of the characteristic sausage shape these stars make when plotted in velocity space. This merger, which occurred approximately 10 billion years ago, delivered roughly 50 billion solar masses to the Milky Way. The mass ratio at the time was approximately 4:1, making it the largest merger our galaxy has experienced in at least the last 10 billion years. Debris from Gaia-Enceladus now dominates the interstellar halo, that roughly spherical cloud of stars extending from about 15,000 to 50,000 light-years from the galactic center. The merger contributed at least 8 globular clusters to the Milky Way, possibly 13, and potentially triggered or enhanced the formation of our galaxy's thick disk. Before the collision, the Milky Way had a thinner disk of stars orbiting more or less in the same plane. When Gaia-Enceladus plowed through, its gravitational influence dynamically heated the precursor disk, stirring up stellar orbits and puffing the disk into a thicker configuration. The thick disk we observe today, extending a few thousand light-years above and below the main galactic plane, bears the imprint of this ancient violence. The Sagittarius dwarf galaxy, still in the process of being disrupted, represents another merger that's been ongoing for billions of years. Its streams wrap the entire sky, contributing to both the northern and southern galactic hemispheres. Each time Sagittarius passes through the Milky Way's disk, it loses more mass to tidal stripping, and its remaining core moves on a gradually decaying orbit. Computer simulations suggest it may have delivered 4 to 5 globular clusters to the Milky Way over the course of its disruption. The Sequoia merger, named after the giant trees, appears to have occurred shortly after Gaia-Enceladus, perhaps 9 to 10 billion years ago. It delivered material on highly radial orbits that reach deep into the galactic center. The Cetus stream, the LMS-1 or Wukong stream, and the Arjuna-Sequoia-Itoi complex represent other identified merger events, each contributing smaller amounts of mass but adding to the complexity of the Milky Way's assembly history. Malhan's team also identified what they called Pontus, a previously unknown merger event, by finding a group of globular clusters and stellar streams with correlated action variables that didn't match any of the previously known mergers. Pontus appears to have been a relatively low-mass dwarf galaxy that merged with the Milky Way several billion years ago, contributing a few globular clusters and a spattering of halo stars. These 6 confirmed mergers don't represent the complete list. The Milky Way has almost certainly consumed dozens of dwarf galaxies over its lifetime, but smaller mergers from lower-mass dwarfs leave fainter traces, harder to distinguish from the general background. The forensic analysis reaches its limit when the debris from ancient, low-mass mergers becomes so dispersed and phase-mixed that it no longer forms recognizable streams. Those dwarfs have achieved complete digestion, their stars fully assimilated into the Milky Way's halo, with no remaining evidence of their separate origins. Yet the evidence we can detect paints a clear picture. The Milky Way grew through cannibalism. The 50 to 60 dwarf galaxies we observe in orbit around us today represent merely those that have survived so far. Many more have already been consumed. Their stars now masquerade as native Milky Way citizens, indistinguishable except through careful chemical and dynamical archaeology. We are a composite entity, built from the bodies of our victims. Recent estimates suggest that approximately 50% of the Milky Way's globular clusters originally formed in dwarf galaxies and were subsequently accreted. If accurate, this means that when you look up at famous globular clusters like Omega Centauri or M54, you're looking at immigrant populations, stellar cities that originated in now extinct realms. Omega Centauri, the largest and brightest globular cluster in the Milky Way, containing about 10 million stars, may itself be the stripped core of a dwarf galaxy, the last dense remnant that resisted complete tidal dissolution. The forensic reconstruction continues. Each new data release from Gaia, each new spectroscopic survey measuring stellar chemistry, each improved computer simulation of merger dynamics adds pieces to the puzzle. The Milky Way's formation history, once opaque, becomes increasingly clear. We're reading a story, written in starlight, deciphering the biography of our galaxy, one chemical fingerprint at a time. 10 billion years ago, the universe looked different. Galaxies were smaller, more numerous, more chaotic. Star formation rates ran higher across the cosmos as gas-rich galaxies collided and merged, converting their hydrogen and helium into new generations of stars. The Milky Way existed, but in a form we would barely recognize. It contained perhaps a quarter of its current stellar mass, arranged in a relatively thin disk, surrounded by a modest, dark matter halo. It had not yet become the grand spiral we inhabit today. Approaching through intergalactic space came another galaxy. Astronomers have no record of its original name, no way to know what its hypothetical inhabitants, if any existed, might have called it. We know it only by the designation Amina Helmi gave it, Gaia-Enceladus, after the giant in Greek mythology, born from the earth and sky. It was a dwarf galaxy, slightly more massive than the small Magellanic Cloud we observe today, containing perhaps 10 billion stars and 50 billion solar masses of total matter, including dark matter. It approached on a retrograde orbit, meaning it was moving against the direction of the Milky Way's rotation. The orbit's inclination was approximately 30 degrees, tilted significantly from the plane of the Milky Way's disk. These orbital parameters matter because they determined what happened next. A prograde orbit, aligned with the disk's rotation, would have produced a gentler merger. A radial orbit, plunging straight toward the galactic center, would have caused more extreme disruption. The specific angle and direction of Gaia-Enceladus's approach created a collision energetic enough to fundamentally reshape the Milky Way, while still allowing both galaxies' stars to mix relatively smoothly. The merger unfolded over hundreds of millions of years. As Gaia-Enceladus fell deeper into the Milky Way's gravitational well, tidal forces began stretching it. Stars on its near side pulled ahead, accelerated by the Milky Way's gravity. Stars on its far side lagged behind, The dwarf galaxy elongated into an ellipsoidal shape, then began to fragment. Its outer stars peeled away first, forming tidal tails that wrapped around the Milky Way. Its core held together longer, protected by its higher stellar density and dark matter concentration. The first passage through the Milky Way's disk was catastrophic for both galaxies. Gaia-Enceladus, already stretched and disrupted, plowed through the Milky Way's gas and stars. Its own gas, compressed by the collision, ignited in bursts of star formation, brief blazes of stellar birth before ram pressure stripped away the remaining fuel. The Milky Way's disk, struck by this intruder from below, experienced dynamical heating. Stars that had been orbiting in nearly circular paths in a thin disk got scattered onto more elliptical, more inclined orbits. The disk puffed up, thickened, as kinetic energy from the merger randomized stellar velocities. Gaia-Enceladus didn't survive the first passage intact. By the time it emerged on the other side of the Milky Way, it was no longer a coherent galaxy. It had become a stream of stars and dark matter following related but distinct orbits. These orbits, highly elliptical and retrograde, carried debris from the inner regions of the Milky Way out to distances exceeding 20 kiloparsecs, then back in toward the center. The galaxy had become a cloud, a swarm, a population sharing a common ancestry but no longer bound by self-gravity. Successive passages, as the debris orbited through the Milky Way repeatedly, spread the material across the entire inner halo. Phase mixing, the gradual dispersion of initially coherent streams into a smooth background, transformed the obvious streams into a more uniform distribution. Today, 10 billion years later, we can identify Gaia-Enceladus stars by their chemistry and kinematics, but they no longer form obvious spatial structures. They've been thoroughly mixed into the Milky Way's fabric. The mass delivered by this merger represented roughly 1/5 of the Milky Way's total mass at that time. This is significant enough to have major consequences. Computer simulations reproducing mergers with similar mass ratios show that they trigger structural changes in the host galaxy. The pre-existing thin disk gets dynamically heated into a thick disk. If the dwarf galaxy contained a central supermassive black hole, and it likely did, that black hole would have eventually spiraled inward and merged with the Milky Way's central black hole, adding to Sagittarius A star's mass. The globular clusters contributed by Gaia-Enceladus remain identifiable today. At least 8 globular clusters, possibly 13, show chemical signatures and orbital properties consistent with having formed in Gaia-Enceladus rather than the Milky Way. These clusters formed in the dwarf galaxy before the merger, survived the merger's violence, and now orbit the Milky Way as permanent immigrants. When you observe these clusters through a telescope, you're looking at stellar populations that originated in another galaxy, stellar cities torn from their homeland and deposited in ours. The chemical evidence provides the most compelling confirmation that this merger actually happened. Stars from Gaia-Enceladus show a distinct sequence when you plot their iron abundance against other elements like magnesium or calcium. This sequence differs from the sequence followed by stars born in the Milky Way. The two populations occupied different regions in chemical abundance space, each reflecting the distinct star formation and chemical enrichment histories of their parent galaxies. When hundreds or thousands of stars all show the same offset from the Milky Way's normal patterns, while simultaneously sharing unusual orbital properties, the conclusion becomes inescapable. They came from somewhere else. The age distribution of Gaia-Enceladus stars clusters around 10 to 11 billion years, with some variation. This suggests the dwarf galaxy formed most of its stars relatively early in cosmic history, perhaps in a burst of star formation when it first assembled, then had a more quiescent later life before the merger. The youngest Gaia-Enceladus stars, those formed during the merger itself from gas compressed during the collision, would be approximately 10 billion years old today. No Gaia-Enceladus stars exist with ages less than that. because the galaxy ceased to exist as a distinct entity after the merger completed. Amina Helmi's recognition of this event in 2018 represented a watershed moment for understanding galactic archaeology. Before Gaia-Enceladus, astronomers suspected the Milky Way had experienced major mergers based on theoretical predictions, but they lacked direct evidence. Stellar streams and chemical anomalies hinted at past accretion events, but nothing on the scale of Gaia-Enceladus had been clearly identified. Its discovery proved that major mergers weren't just theoretical possibilities, they had actually happened. The Milky Way's history included episodes of violent restructuring. More broadly, the discovery validated hierarchical models of galaxy formation, with major mergers becoming rarer at later cosmic times as galaxies grew larger and separated by greater distances. The fact that the Milky Way's last major merger occurred 10 billion years ago, in the first quarter of cosmic history, matches those predictions. Since then, the Milky Way has continued growing through minor mergers and cannibalism of dwarf galaxies, but nothing as significant as Gaia-Enceladus has collided with us. The merger fundamentally shaped the Milky Way we observe today. Without Gaia-Enceladus, our galaxy would be smaller, perhaps 20% less massive. Our thick disk might not exist, or would be less prominent. Our inner stellar halo would be much less populated. Several of our globular clusters would orbit in other galaxies. The Milky Way's structure bears the permanent imprint of this ancient collision. We are partially made from the body of Gaia-Enceladus. Some of the stars overhead, stars we count as part of our galaxy, were born in another realm and violently transplanted here billions of years before the Sun existed. If the Milky Way represents a moderately cannibalistic galaxy, having consumed perhaps a few dozen dwarf galaxies over its lifetime, then the galaxies that crown the centers of rich galaxy clusters represent cannibalism taken to its ultimate extreme. These are the monsters of the universe, the supermassive elliptical galaxies that have spent billions of years systematically devouring their neighbors. Galaxy clusters contain hundreds to thousands of galaxies bound together in a region spanning several million light-years. The Virgo cluster, the nearest large cluster to us, lies about 54 million light-years away and contains over 1,300 identified galaxies. The Coma cluster, lying 300 million light-years away, contains over 1,000 bright galaxies and probably thousands more dim dwarf galaxies that are harder to detect. These clusters represent the largest gravitationally bound structures in the universe. Only superclusters, loose associations of multiple clusters, span larger volumes, and superclusters are not generally gravitationally bound as coherent entities. At the center of most rich galaxy clusters sits a particular type of galaxy that astronomers designate as the brightest cluster galaxy, or BCG. The name is definitional. It's simply the brightest galaxy in the cluster. But BCGs share enough common properties that they constitute a distinct class of object. They are almost invariably giant elliptical galaxies, enormous systems containing hundreds of billions to over 1 trillion stars. They sit at or very near the geometric center of their host cluster, positioned at the bottom of the cluster's gravitational potential well. They are often surrounded by extended envelopes of diffuse starlight, stretching hundreds of thousands of light-years from their cores, giving them a characteristic CD galaxy morphology, where the C stands for supergiant and D for diffuse envelope. M87 in the Virgo cluster provides the canonical nearby example. This galaxy, lying at the heart of the nearest large cluster, contains several trillion stars distributed across a region 420,000 light-years in diameter. For comparison, the Milky Way spans about 100,000 light-years. M87 dwarfs us. Its central supermassive black hole contains approximately 6.5 billion solar masses, more than 1,000 times the mass of our Sagittarius A star. This black hole became famous in 2019 when the Event Horizon Telescope collaboration produced the first direct image of a black hole's shadow, that dark circle surrounded by the glowing accretion disk. BCGs form through a process that represents galactic cannibalism at industrial scale. Early in a cluster's history, it contains many galaxies of various sizes, all orbiting within the cluster's shared dark matter halo. Those galaxies interact gravitationally, dynamical friction, the same process that causes dwarf galaxies to spiral inward in the Milky Way's halo, causes the most massive cluster galaxies to lose orbital energy and sink toward the cluster center. As they do so, they encounter other galaxies. Some of these encounters are major mergers between comparable mass galaxies. More commonly, they're minor mergers or outright cannibalism events where the sinking giant consumes smaller galaxies it encounters. Over billions of years, this process feeds the central galaxy, like a snowball rolling downhill, accumulating mass as it descends. The BCG grows by systematically incorporating every galaxy it encounters. The cannibalism is facilitated by the dense environment. In a rich cluster, galaxies pass close to each other frequently. The BCG, positioned at the center where galaxy density peaks, has the maximum opportunity for encounters. Every galaxy that falls into the cluster center eventually ends up incorporated into the BCG's structure. The visible evidence of this cannibalism appears in the morphology of many BCGs. NGC 1316, a giant elliptical in the Fornax cluster, shows dark dust clouds silhouetted against its glowing core. Elliptical galaxies normally contain almost no dust. The dust in NGC 1316 almost certainly came from a smaller, gas-rich galaxy that the giant cannibalized roughly 100 million years ago. The gas has been stripped away or consumed, but the dust remains as temporary evidence of the meal. NGC 6240 shows an even more dramatic example. It has two nuclei visible in its core, the remnants of two galaxies that merged to form it. Both nuclei contain supermassive black holes, which will eventually merge themselves once they've spiraled close enough together. Computer simulations of cluster formation reproduce the growth of BCGs through this cannibalistic process. Starting from initial conditions based on cosmological models, the simulations follow the evolution of dark matter, halos, gas, and stars over billions of years. They show that the most massive halo in a cluster naturally attracts smaller halos through gravity. When those halos merge, their galaxies merge too. The central galaxy in the simulation grows steadily, accumulating mass from its victims, while its structure transforms from whatever it started as into a massive elliptical. The transformation happens because multiple mergers destroy ordered rotation. A spiral galaxy, like the Milky Way, is characterized by stars orbiting in roughly the same plane, moving in the same direction, creating the spiral pattern through density waves. When such a galaxy merges with another galaxy on a different orbital plane, the collision scrambles the neat rotation. Stars get flung onto orbits with random orientations. After several mergers, the resultant galaxy contains stars moving in every possible direction, with no preferred plane or sense of rotation. This is the defining characteristic of an elliptical galaxy. Its stars orbit through the galaxy in a disorganized swarm, supported against gravitational collapse by their random velocities rather than by organized rotation. BCGs often show alignment between their major axes and the major axes of their host clusters. If you measure the orientation of the BCG's elongated shape and compare it to the elongated distribution of galaxies in the cluster, they tend to point in similar directions. This alignment persists even at high redshifts, in clusters observed when the universe was less than half its current age. The alignment suggests that BCGs and their clusters formed together. with the same large-scale tidal fields that shape the cluster's overall structure, also influencing the BCG's assembly. The stellar populations in BCGs tell a story of early, intense star formation followed by quiescence. Most BCGs contain primarily old, red stars, with ages exceeding 10 billion years. This indicates that the bulk of their stellar mass formed early in cosmic history, when the universe was younger and more gas-rich. Recent studies using deep observations find no significant evolution in BCG sizes or luminosities since a redshift of approximately 1.5 to 2, corresponding to look-back times of 9 to 10 billion years. This implies that most BCGs assembled their stellar mass early and have grown relatively little since then, at least through star formation. Yet, they have continued growing in total mass through dry mergers between galaxies that have already converted most of their gas into stars or expelled it. When two gas-poor galaxies merge, they don't trigger much new star formation because there's no gas to collapse into new stars. Instead, they simply add their stellar populations together, creating a larger galaxy without changing the average age or color of the stars. Dry mergers allow BCGs to continue growing without undergoing starburst episodes that would create young, blue stars inconsistent with their observed, red, evolved populations. Not all BCGs follow this pattern. A subset show strong ongoing star formation, in some cases forming hundreds of solar masses worth of new stars every year. The Phoenix cluster, at a redshift of 0.597, contains a BCG forming approximately 740 solar masses of stars per year, an extraordinarily high rate. This star formation is fueled by a process called a cooling flow. The galaxy sits in the middle of dense, hot intracluster gas that glows in X-rays. That gas radiates energy and cools. As it cools, it becomes denser and falls toward the cluster center. If nothing counteracts this process, the cooling gas accumulates around the BCG and collapses into knots of star formation. Most BCGs don't show such vigorous star formation, which implies something usually counteracts the cooling flow. The leading explanation is feedback from the central supermassive black hole. As gas falls toward the BCG's center, some of it gets accreted onto the black hole. This accretion powers jets and radiation that heat the surrounding gas, preventing it from cooling and collapsing. The system reaches a quasi-steady state where cooling is balanced by heating, preventing runaway star formation. Phoenix cluster and similar systems represent cases where the balance has tipped temporarily toward cooling, perhaps because the black hole feedback hasn't yet had time to respond to a recent influx of gas. The extended halos around CD galaxies represent another signature of cannibalism. These halos contain stars distributed across hundreds of thousands of light years, far larger than typical galaxies. The current interpretation holds that these stars were stripped from galaxies during the early stages of tidal disruption, before those galaxies fell all the way into the core and merged with the central galaxy. The stripped stars remain on wide orbits around the BCG, forming a diffuse envelope that gradually phase mixes into a smooth distribution. The halo is essentially a fossil record of past meals, the bones left scattered around the feast. Recent observations have found examples that challenge the standard picture. A small number of superluminous spiral galaxies have been identified at the centers of galaxy clusters. These shouldn't exist according to traditional understanding, because the multiple mergers required to grow a BCG should destroy any spiral structure. The leading explanation for these anomalous objects proposes they're actually elliptical BCGs that recently merged with a gas-rich galaxy, and that merger delivered enough gas to reform a disk. The massive bulges in these spiral BCGs support this interpretation, suggesting they have the elliptical cores expected of BCGs with newly reformed disks around them. The masses of BCGs can exceed 100 trillion solar masses, making them the most massive individual galaxies in the universe. Their sizes can reach 1,000,000 light-years or more when you include the extended halos. Their central black holes range from hundreds of millions to tens of billions of solar masses. They represent the endpoint of hierarchical growth. Galaxies that have cannibalized so many neighbors over billions of years that they've grown into true cosmic leviathans. Yet even these giants continue growing. The process hasn't stopped. Galaxies continue falling into cluster centers, continue being tidally stripped and consumed. The BCGs we observe today are larger than BCGs observed at high redshift, indicating they've grown over cosmic time, even if primarily through dry mergers rather than star formation. In the future, as cluster dynamics continue driving galaxies toward cluster centers, these giants will grow larger still, accumulating ever more mass from their surroundings. The cannibalism is ongoing, patient, inexorable. The universe keeps receipts. Every merger, every cannibalism event, every dwarf galaxy consumed leaves evidence that persists for billions of years. Reading this evidence requires combining observations across multiple wavelengths and techniques, but the story it tells is increasingly clear. Galaxies grow through violence, and that violence is written in their structures. Stellar streams provide the most obvious signatures. These coherent structures, formed from stars stripped during tidal disruption, wrap around host galaxies like ribbons. The streams are cold, meaning the stars within them have very similar velocities, and this coldness persists for surprisingly long periods. Computer simulations show that streams can remain identifiable for several billion years after their progenitor dwarf galaxy has been completely disrupted. Eventually, phase mixing disperses the stream into the general halo background, but the process takes time. During that time, the stream serves as direct evidence of a past merger. Dozens of stellar streams have been identified in the Milky Way's halo using data from surveys like the Sloan Digital Sky Survey and the Gaia mission. Each stream has a distinct orbit, chemical composition, and stellar population. Some have been conclusively linked to specific progenitor galaxies. The Sagittarius stream clearly originates from the Sagittarius dwarf galaxy because we can trace it directly back to that galaxy's current location. Other streams, like the Orphan stream or the Monoceros ring, have no identified progenitors. They're orphans in the most literal sense, the remains of dwarf galaxies that have been completely consumed, with only their tidal debris surviving as evidence they ever existed. Chemical composition provides the second major line of evidence. Every star preserves a record of the gas cloud from which it formed. By measuring the abundances of elements like iron, magnesium, calcium, and rare earth elements in stellar atmospheres, astronomers can reconstruct the chemical enrichment history of that star's parent galaxy. Different galaxies have different enrichment histories based on their mass, star formation rate, and age. These differences persist even after the galaxies merge. The Apogee survey, which has measured detailed chemical abundances for hundreds of thousands of stars, has been instrumental in identifying chemically distinct populations in the Milky Way. Stars from Gaia-Enceladus form a distinct sequence when you plot magnesium abundance against iron abundance. Stars from other accreted dwarfs form other sequences. Even billions of years after the merger, even after the stars have been spatially mixed throughout the halo, their chemistry preserves evidence of their separate origins. Age dating adds a third dimension. By measuring a star's position on the Hertzsprung-Russell diagram and comparing it to stellar evolution models, astronomers can estimate when that star formed. Stars from a dwarf galaxy that stopped forming stars 10 billion years ago will all be older than 10 billion years. Stars from a dwarf galaxy that had ongoing star formation until it was tidally disrupted 5 billion years ago will show a range of ages up to 5 billion years. The age distribution of an accreted population provides clues about when the merger occurred and whether the dwarf galaxy was actively forming stars at that time. Globular clusters serve as particularly useful tracers. These dense, spherical clusters, containing hundreds of thousands to millions of stars, formed early in cosmic history and have remained relatively intact since then. Many globular clusters originated in dwarf galaxies and were subsequently accreted by the Milky Way. They can be identified as accreted objects through their orbits and chemical properties. An accreted globular cluster typically orbits on an eccentric path that takes it far from the galactic plane, reflecting the dwarf galaxy's orbit rather than the Milky Way's rotation. Its stellar population often shows chemical peculiarities distinct from Milky Way-born globular clusters. Recent estimates suggest that approximately 50% of the Milky Way's globular clusters originated in dwarf galaxies. This percentage astonishes many astronomers because it implies that a substantial fraction of what we consider the Milky Way's native population actually immigrated from elsewhere. Clusters like Omega Centauri, with its unusual multiple stellar populations and complex chemical patterns, almost certainly formed in a dwarf galaxy. Some researchers argue that Omega Centauri is itself the stripped core of a dwarf galaxy, the densest, most tightly bound central region that survived tidal disruption when the rest of the galaxy was shredded. In galaxy clusters, the evidence appears in the intracluster light, or ICL. This is starlight that doesn't belong to any particular galaxy. Instead, it's emitted by stars floating freely in the space between galaxies, dispersed throughout the cluster. Deep imaging of galaxy clusters reveals this faint, diffuse glow extending across millions of light years. The ICL represents stars that have been tidally stripped from cluster galaxies but haven't yet been incorporated into the BCG. They're in the process of being cannibalized, currently drifting in intergalactic space, gradually mixing and eventually either accreting onto the BCG or remaining dispersed. The amount of ICL in a cluster correlates with the cluster's dynamical state. Young, recently assembled clusters have less ICL because tidal stripping hasn't had as much time to redistribute stars. Older, more relaxed clusters have more ICL, sometimes containing as much stellar mass in the ICL as in the BCG itself. This suggests that tidal stripping and galaxy cannibalism are ongoing processes that continuously move stellar mass from individual galaxies into the intergalactic medium. Morphological disturbances provide additional evidence. Galaxies that have experienced recent mergers often show disturbed shapes. Tidal tails extending from their bodies, shells of stars surrounding them, arcs and ripples in their light distribution. These features form when two galaxies merge and their stellar populations haven't yet relaxed into a smooth configuration. Computer simulations show that such features persist for roughly 1 billion years after a merger, gradually fading as the star's orbits circularize and the system reaches dynamical equilibrium. Shell galaxies provide particularly clear examples. The shells form when a small galaxy falls into a larger one and gets tidally disrupted. The shells represent stars stripped at different times during the merger, spread out into layers by the complex dynamics of the collision. By measuring the shell's positions and brightnesses, astronomers can reconstruct when the merger occurred and estimate the mass of the consumed galaxy. Kinematic evidence appears in the velocity dispersions and rotation curves of galaxies. A galaxy that has experienced multiple mergers will show kinematically distinct components, populations of stars with different velocity distributions. The Milky Way's thick disk rotates slower than the thin disk, a signature that it formed differently, likely through the dynamical heating caused by the Gaia-Enceladus merger. The stellar halo shows little organized rotation, consistent with it being an accretion-dominated structure built primarily from disrupted dwarf galaxies that fell in from random directions. Modern cosmological simulations that follow galaxy formation from the early universe to today reproduce all these signatures. The simulations show that in a hierarchical universe where structure grows from small to large, mergers and cannibalism are inevitable. Gravity drives systems together. Small galaxies merge to form larger ones. Those larger galaxies continue accreting smaller companions. The process continues across cosmic time, with the merger rate decreasing as galaxies grow larger and more widely separated, but never stopping entirely. The illustrious simulation, one of the most sophisticated cosmological simulations performed, followed the evolution of a representative volume of the universe from shortly after the Big Bang until today. It included dark matter, gas, stars, and black holes, along with models for star formation, supernova feedback, and black hole feedback. When researchers analyzed the simulated Milky Way-like galaxies in the illustrious volume, they found that all of them had experienced significant mergers in their pasts. The simulated galaxies showed stellar halos built from accreted satellites, thick disks formed through dynamical heating, and central supermassive black holes grown through mergers and gas accretion. The agreement between simulation and observation validates the hierarchical paradigm. The evidence we observe in the Milky Way's halo, the streams and chemical anomalies, and accreted globular clusters, matches what simulations predict should exist if galaxies grow through mergers and cannibalism. This doesn't prove the paradigm correct in all details, but it strongly supports the broad picture. Galaxies are not primordial objects that formed complete at high redshift. They're composite structures built over billions of years through continuous assembly, with major mergers early in their histories and ongoing accretion of smaller satellites continuing to the present day. Remaining mysteries persist. We don't know the complete merger history of the Milky Way. Some accreted satellites have been completely phase mixed and are no longer distinguishable as separate populations. The total number of dwarf galaxies the Milky Way has consumed remains uncertain, with estimates ranging from dozens to possibly hundreds if you include very low-mass systems. The connection between mergers and the growth of central supermassive black holes remains incompletely understood. The role of dark matter, which dominates the mass of both galaxies and their satellites, continues to be probed through increasingly sophisticated simulations and observations. But the fundamental picture is clear. We inhabit a galaxy built through cannibalism. The stars overhead include immigrants from other realms. The globular clusters contain populations formed in galaxies that no longer exist. We are living in the ruins of smaller galaxies, and those ruins are also our foundation. The Andromeda Galaxy, also known as M31, appears as a faint smudge of light in the autumn sky of the northern hemisphere. To the naked eye under dark skies, it looks like a small, fuzzy patch in the constellation Andromeda, spanning roughly the width of the full moon. Through a telescope, it resolves into a magnificent spiral, tilted at an angle so we see it nearly edge-on, its spiral arms traced out in dust lanes and glowing nebulae. It lies 2.5 million light-years away, the nearest large spiral galaxy to our own. It's also falling toward us at 110 kilometers per second. This has been known since the 1920s, when Vesto Slipher measured the Doppler shift of Andromeda's light and found it blue shifted, indicating the galaxy was approaching rather than receding as most distant galaxies do. For decades, this measurement remained a curiosity, a peculiarity of local motion overshadowed by the cosmic expansion that carries more distant galaxies away from us. Then, in the early 21st century, astronomers used the Hubble Space Telescope to measure Andromeda's sideways motion across the sky, its proper motion with sufficient precision to calculate its full three-dimensional velocity vector. The initial conclusion seemed inescapable. In 2012, detailed analysis of Hubble observations suggested the galaxies would collide in approximately 4 to 5 billion years. For over a decade, this prediction dominated our understanding of the Milky Way's future. Simulations showed the collision unfolding in spectacular detail, two spiral galaxies intertwining and ultimately merging. But the universe resists simple predictions. In 2025, a comprehensive new study using more than a decade of Hubble data combined with precise measurements from the Gaia spacecraft revealed something unexpected. The situation is far more uncertain than astronomers had believed. When researchers accounted for all observational uncertainties and included the gravitational influences of other local group members, particularly the large Magellanic Cloud and the Triangulum Galaxy, the certainty evaporated. The new analysis suggests there's approximately a 50% chance of collision within the next 10 billion years. The probability of the previously predicted head-on collision in 4 to 5 billion years? Only about 2%. The reason for this dramatic revision comes down to the difficulty of measuring cosmic motions with sufficient precision. Andromeda is indeed approaching us at 110 kilometers per second along the line of sight. That radial velocity is relatively easy to measure through Doppler shift, but determining how fast it's moving sideways, perpendicular to our line of sight, requires measuring its apparent motion across the sky. At a distance of 2.5 million light-years, even substantial sideways velocities translate to almost imperceptible angular motions. It's like trying to measure the growth rate of human hair from the distance of the moon, as one astronomer described it. The updated measurements show Andromeda has a small but significant sideways velocity. Combined with uncertainties in the masses of both galaxies and the gravitational effects of nearby companions, this creates a range of possible futures. In roughly half the simulations, the two galaxies make a close pass, separated by around 500,000 light-years or less. They swing past each other, move outward, then gradually spiral back inward over billions of years through a process called dynamical friction, eventually merging in the far future, perhaps 8 to 10 billion years from now. In the other half of simulations, the galaxies don't come close enough for dynamical friction to be effective. They continue their orbital dance for an indefinite period, perhaps never merging at all. This uncertainty doesn't diminish the significance of what may happen should a collision occur. If Andromeda and the Milky Way do merge, this will not be cannibalism. Andromeda contains roughly 1 trillion stars, more than twice the Milky Way's 400 billion. Its total mass, including dark matter, slightly exceeds ours, making the mass ratio close to 2 to 1. This qualifies as a major merger, a collision between galaxies of comparable size. The outcome will be fundamentally different from the minor mergers and cannibalism events that have characterized the Milky Way's recent history. Computer simulations that model potential collision scenarios show a multi-stage process that would unfold over several billion years. The first passage would occur when the galaxy's outer edges first intersect. Tidal forces would begin deforming both galaxies, pulling stars out into tidal tails. The galaxies wouldn't merge on this first passage. They would be moving too fast, and they would pass through each other, emerging on opposite sides with dramatically altered structures. But they would remain gravitationally bound. Their mutual gravity would sap orbital energy, and they would begin falling back toward each other. The second passage, a few 100 million years after the first, would involve more direct interaction. The galaxies would interpenetrate more deeply. More stars would get scattered onto new orbits. More gas would get compressed, triggering bursts of star formation. The galaxies would begin to lose their individual identities, their structures merging into a chaotic amalgamation. Multiple passages would follow over the next billion or two, each further scrambling the galaxy's structures. Eventually, dynamical friction would dissipate enough orbital energy that the galaxies would no longer have sufficient velocity to escape each other. They would settle into a single, merged system. The simulations show this final product would be a giant elliptical galaxy, all traces of spiral structure erased by the violent scrambling of the merger. Astronomers have jokingly named this hypothetical future galaxy Milky Way, a portmanteau of Milky Way and Andromeda. What would this mean for the solar system if such a merger were to occur? Almost certainly nothing catastrophic. The probability that the Sun will physically collide with another star during a merger approaches zero. Stars are too far apart, galaxies too much empty space. However, the Sun's orbit around the galactic center would be significantly altered. Currently, we orbit at a radius of about 8 kiloparsecs, roughly 26,000 light-years from the galactic center, completing one orbit every 230 million years. A merger would scatter us onto a different orbit, possibly carrying us into the outer regions of Milky, far from the merged galaxy's center, or possibly dropping us closer in. Earlier simulations of galactic mergers suggested there's a 10 to 20% chance the solar system could be ejected entirely during such an event, flung into intergalactic space by a close gravitational encounter with a massive star cluster or by tidal forces. If this were to happen, we would drift through the darkness between galaxies, no longer part of any galactic structure. The night sky from Earth would contain no Milky Way band, no nearby spiral arms, just scattered distant galaxies receding into the cosmic expansion, assuming Earth still exists at that point, which is uncertain for other reasons. The Sun's evolution will reach a critical point around the same time as any potential merger. In approximately 5 billion years, the Sun will exhaust the hydrogen fuel in its core and begin burning hydrogen in a shell around a helium core. This will cause it to expand into a red giant, increasing in radius until it may engulf Mercury and Venus. Earth's fate during this phase remains debated. We might be consumed by the expanding Sun, or we might survive at the edge of the Sun's envelope, subjected to searing heat that will boil away our oceans and atmosphere. Either way, Earth becomes uninhabitable long before any Milky Way-Andromeda merger would complete. So a potential merger doesn't threaten Earth's habitability directly. The Sun's evolution does that on its own schedule. The merger, if it occurs, simply determines what the night sky will look like during the red giant phase, assuming anyone or anything is around to see it. Instead of the Milky Way's spiral arms, the sky might be dominated by the bright core of Milkomeda and the chaotic star-forming regions created by compressed gas in the merger. Or, if the galaxies pass without merging, the night sky might show both Andromeda and the Milky Way as distinct structures, gradually receding from each other after their closest approach. The Triangulum galaxy, M33, may participate in these events. This smaller spiral galaxy, the third largest member of the local group after Andromeda and the Milky Way, currently orbits at the edge of the local group. The 2025 study found that Triangulum's gravitational influence, along with that of the Large Magellanic Cloud, significantly affects the probability of an Andromeda-Milky Way collision. Some simulations show Triangulum colliding with the Milky Way or Andromeda before those two galaxies merge with each other. Other simulations show it avoiding the main collision and surviving as a separate galaxy. Its fate depends sensitively on its current position and velocity, parameters that remain somewhat uncertain. The Magellanic Clouds add further complexity. If they're in bound orbits, they'll eventually be consumed by the Milky Way regardless of what happens with Andromeda. If they escape after their current passage, they might avoid consumption entirely, or they might be captured by Andromeda during any merger chaos, becoming satellites of the larger galaxy instead of ours. The three-body or four-body dynamics of multiple massive galaxies interacting simultaneously produces complex outcomes difficult to predict precisely. For astronomers living billions of years in the future, assuming such beings exist, the outcome will provide spectacular observational opportunities regardless of whether the galaxies merge or pass. If they do merge, nearby starbursts, triggered by gas compression, will blaze across the sky. Active galactic nuclei, possibly including merged supermassive black holes from both galaxies' centers, will produce jets and radiation visible across the electromagnetic spectrum. The process of watching two galaxies merge from inside the collision will offer perspectives impossible to obtain any other way. If they pass without merging, the slow gravitational dance and near miss will itself be extraordinary to witness. But for us, frozen in this particular moment billions of years before any potential collision, the uncertainty itself serves as a reminder that even our best predictions about cosmic futures remain tentative. We observe the galaxy's current motions. We measure their masses as precisely as current technology allows. We run sophisticated simulations. Yet the outcome remains genuinely uncertain. Our galaxy's fate is not written in stone. It depends on initial conditions we cannot measure with perfect precision and on the gravitational influences of every massive object in the local group. What we can say with confidence is that the processes we observe in distant galaxies are not abstract phenomena. Whether through direct collision or through continued cannibalism of smaller satellites, the Milky Way will continue evolving. Our galaxy's history of mergers and accretion, which we read in the debris of past collisions, extends into a future that holds either dramatic transformation through major merger or continued gradual growth through consuming dwarf galaxies. We are not the endpoint of evolution, but a temporary configuration, one stage in an ongoing process of assembly and transformation that will continue long after our sun dies. There's a paradox at the heart of galactic cannibalism. By any reasonable definition, it's violent. Galaxies collide at velocities of hundreds of kilometers per second. Tidal forces rip them apart. Stars get scattered, gas clouds compressed, entire structures destroyed. Yet this violence creates the universe's most beautiful and complex objects. The resolution lies in the timescales involved. A typical galactic merger unfolds over 500 million to 2 billion years. On human timescales, this is effectively eternal. Entire civilizations could rise and fall during a single orbital period of a merging dwarf galaxy. Species could evolve and go extinct. Stars could form, burn through their nuclear fuel, and die. To any inhabitants of the merging galaxies, assuming they existed and achieved sufficient technological sophistication to notice, the merger wouldn't appear as an event, but as a permanent condition, a feature of the universe, as unchanging as the laws of physics themselves. From this perspective, galactic violence becomes gentle. Individual stars almost never experience close encounters during mergers. They simply find themselves, over millions and billions of years, moving in different orbits within a reconfigured galaxy. A star that began its life in a dwarf galaxy orbiting the Milky Way ends its life as part of our halo, having transitioned gradually through a series of orbits, each slightly different from the last. The change is real, but so slow as to be imperceptible to anything living on timescales shorter than geological. The gas experiences more dramatic violence. When gas clouds collide at supersonic velocities, they create shock waves that heat and compress the gas. But this violence serves creation. The compression makes the gas dense enough to collapse under its own gravity, fragmenting into clumps that become protostars. The merger-induced starburst represents birth, not death. The violence converts potential energy stored in separated gas clouds into kinetic energy, radiation, and ultimately into the nuclear burning of stars. It's destructive only in the sense that the original gas cloud structures are destroyed, but that destruction enables the formation of something more complex. This pattern, destruction enabling creation through transformation, operates at every scale in the universe. Hydrogen and helium from the Big Bang couldn't form complex chemistry until some of that hydrogen underwent nuclear fusion in stars, producing heavier elements. But those heavier elements remained locked inside stars until supernovae violently dispersed them into space. The supernova's violence was necessary for the enrichment of the interstellar medium that eventually formed planets, life, us. Every atom of carbon in your body, every atom of oxygen you breathe, was forged in stellar furnaces and liberated by stellar death. Galactic cannibalism operates on the same principle. Small galaxies merge to form larger ones. Larger galaxies continue growing through continued mergers and accretion. The process builds complexity hierarchically, from simple proto-galaxies in the early universe to the grand spirals and giant ellipticals we observe today. Nothing is truly destroyed. Stars that form in a dwarf galaxy continue existing after that galaxy is consumed. They simply become part of a larger structure, their individual existence unchanged, even as their collective context transforms. The universality of this process deserves emphasis. The Milky Way is not unusual in its history of cannibalism. Most large galaxies have consumed dozens to hundreds of smaller companions over their lifetimes. The giant ellipticals in cluster centers represent the extreme endpoint, having cannibalized so many neighbors they've grown into true cosmic leviathans. But even modest galaxies like ours participate in the same fundamental process. Growth through incorporation is the rule, not the exception. This means we are composite beings on multiple levels. The atoms in our bodies were forged in stars. Those stars formed in galaxies. Some of those galaxies were subsequently consumed by other galaxies. We contain materials that have been through multiple cycles of stellar birth, death, and rebirth, and that have belonged to multiple different galactic systems over cosmic history. The iron in your blood might have formed in a star in what is now the Gaia-Enceladus debris 10 billion years ago, in a galaxy that no longer exists except as a population of immigrant stars scattered through our halo. The thick disk of the Milky Way, the population of stars orbiting a few thousand light-years above and below the thin disk, formed through the dynamical heating caused by the Gaia-Enceladus merger. We don't orbit in the thick disk. Our solar system belongs to the thin disk, but the thick disk is part of our galactic environment. When you look at stars in certain directions, you're looking at stars whose orbital properties were determined by that ancient collision. The structure of our galaxy, which determines where stars form and therefore where planets form and therefore where life might arise, was shaped by mergers. Some of the globular clusters visible in the night sky formed in other galaxies. When you point a telescope at Omega Centauri or M54, you're observing stellar populations that originated elsewhere and immigrated here through violent tidal stripping. Those clusters survived the destruction of their parent galaxies and now orbit the Milky Way as permanent residents, indistinguishable in their current behavior from clusters that formed in the Milky Way, but carrying in their chemistry and structure the indelible signature of foreign origins. This leads to a philosophical question about identity. Is the Milky Way the same galaxy it was 10 billion years ago, before the Gaia-Enceladus merger? It contained different stars. It had a different mass, a different structure. If a galaxy's identity is defined by its constituent stars and their arrangement, then the Milky Way is a different entity. But if identity persists through change, if a galaxy remains itself despite incorporating new material and reconfiguring its structure, then we inhabit the same galaxy that existed 10 billion years ago, merely evolved and grown. Perhaps the question itself is misconceived. Galaxies are not static objects but processes, flows of matter and energy temporarily organized by gravity and angular momentum. The Milky Way is not a thing but a happening, a region of space where matter has accumulated and organized itself into a rotating disk of stars and gas. The matter changes. New material gets incorporated through mergers and accretion. Old material gets expelled through supernovae and stellar winds. But the process continues, and we give that continuing process a name, calling it the Milky Way as if it were a fixed entity. On the longest timescales, even galaxies are temporary. The cosmic expansion that carries distant galaxies away from us will eventually separate the local group from the rest of the universe. In trillions of years, after all the mergers have completed, after the Milky Way and Andromeda and Triangulum have combined into Milkomeda, after all the dwarf galaxies have been consumed, the local group will become isolated. The other galaxy groups and clusters will have receded beyond the cosmic horizon, carried by expansion so far that their light can never reach us. Milkomeda will drift alone through an expanding void, the only galaxy visible to any inhabitants, if any exist. Eventually, star formation will cease as galaxies exhaust their gas supplies. The remaining stars will age and die. White dwarfs will cool to black dwarfs. Neutron stars will radiate away their heat. Black holes will evaporate through Hawking radiation over timescales of 10–100 years. The universe will approach a state of maximum entropy, a cold, dark void containing only the most stable particles and the attenuated radiation of black hole evaporation. Even galaxies, these great structures that took billions of years to assemble through mergers and cannibalism, will eventually dissolve into constituent particles. But that endpoint lies so far in the future that it has no bearing on the present. For now, on this night, we inhabit a universe in its prime. Galaxies still contain gas and form stars. Mergers still sculpt galactic structures. We live in what might be called the stelliferous era of cosmic history, the age when stars dominate, when the universe blazes with light generated by nuclear fusion in stellar cores. This era will last trillions of years, thousands of times longer than the universe has existed so far. Within this era, galactic cannibalism serves as one of the primary mechanisms of evolution and growth. It's not gentle by human standards, but on cosmic scales it represents a form of construction, the universe building complexity through incorporation and transformation. We are witnesses to this process and participants in it, living in a galaxy that grew through consuming others and that will itself be consumed in the future merger with Andromeda. Tonight, if you stand under dark skies far from city lights and look up, you're seeing the consequences of billions of years of galactic cannibalism. Those stars overhead, arranged in familiar constellations that have guided human navigation and imagination since our species learned to look skyward, represent a mixture of native Milky Way stars and immigrants from consumed dwarf galaxies. You can't distinguish them with your naked eyes. They all look like stars, points of light varying in brightness and color, but they carry within them the history of our galaxy's violent growth. We know our galaxy has consumed at least 6 or 7 confirmed dwarf galaxies, whose debris we can identify through careful analysis. Gaia-Enceladus, the most massive, delivered 50 billion solar masses 10 billion years ago. Sagittarius continues being shredded in real time, its streams wrapping our sky. Sequoia, Cetus, Pontus, and others contributed their masses over cosmic history. The true number is almost certainly higher. Smaller mergers from lower mass dwarfs have been completely phase mixed, their evidence dispersed into the general halo population beyond our ability to distinguish them. The Milky Way built itself through patient accumulation, adding mass from every dwarf galaxy that wandered too close. The process continues. The Magellanic Clouds, visible from the southern hemisphere as bright patches of light, are falling toward us. Their tidal streams already extend across hundreds of thousands of light years. Whether they escape after this passage or remain bound to us, whether they're eventually consumed or flee to intergalactic space, they will never be the same galaxies they were before encountering us. They've been fundamentally altered by the interaction, and so have we. Their gravitational influence disturbs the Milky Way's disk, creating ripples and perturbations that propagate through our structure. We are changing each other. Our future includes possible transformation on a scale difficult to comprehend. Whether through a major merger with Andromeda or through continued gradual accumulation of smaller galaxies, the Milky Way will not remain as it is. If the Andromeda merger occurs, both galaxies will be transformed into a single giant elliptical. The Milky Way will cease to exist as a distinct entity. Its stars will be redistributed throughout Milkomeda. Its spiral structure, that beautiful pattern of arms, traced out by dust lanes and glowing nebulae, will be destroyed by the merger's violence. Future astronomers studying Milkomeda, if any exist, will be able to read in the orbits and chemistry of its stars the fact that it formed from a merger between two spirals. But the spirals themselves will be gone, existing only as archaeological traces. If instead the galaxies pass without merging, the Milky Way will continue its existence, but forever changed by the close encounter, its structure perturbed, its satellite system potentially rearranged. This is the nature of cosmic time. Everything flows, transforms, becomes something else. Galaxies merge and reform. Stars condense from gas clouds, burn their fuel, return that material to space through winds and supernovae. The returned material forms new stars, new planets, potentially new life. The cycle repeats on timescales so long they mock human comprehension. 1 billion years is difficult to grasp emotionally, even though we can write it easily. 10 billion years, the age of the Gaia-Enceladus merger, exceeds our intuitive sense of duration so completely it becomes mere abstraction. Yet we live in the consequences of those ancient events. The thick disk beneath our feet formed through dynamical heating from that merger. Some of the globular clusters we observe originated in consumed dwarf galaxies. The stellar halo surrounding us contains immigrants from multiple realms. Our galaxy is not pure or pristine, but composite, built from pieces of many smaller galaxies, each piece still carrying chemical and kinematic signatures of its separate origin to be read by those with eyes to see. There's something profound in this realization. We are not separate from the processes we study. We are embedded in them, products of them. The atoms in our bodies cycled through multiple stars. The sun formed from gas clouds enriched by previous generations of stellar death. The Earth condensed from material in the protoplanetary disk. That disk formed from the interstellar medium. That medium was enriched by supernovae. Those supernovae mark the deaths of massive stars. Those stars formed in galaxies that grew through mergers and cannibalism. We are connected to the furthest reaches of cosmic history through this chain of transformation. Understanding galactic cannibalism changes how we see the night sky. Those stars are not eternal fixtures, but temporary configurations, populations that will be redistributed by future mergers. The Milky Way's band of light spanning the sky represents not a permanent feature, but one moment in an ongoing process of assembly. In the future, after the Andromeda merger, beings standing on worlds orbiting stars in Milkomeda will see a different sky, one dominated by the bright elliptical core of their merged galaxy, rather than a spiral disk edge-on. They'll have lost what we have, but they'll have gained something too. The perspective of living in a galaxy that recently underwent a major merger, with all the starburst regions and tidal features and complex structures that entails. This is worth sitting with for a moment. The universe is not static. It wasn't created complete and unchanging. It evolves, grows, transforms through processes that operate on timescales so long they appear eternal to us, but are merely slow from a cosmic perspective. Galaxies are not primordial objects, but evolved structures, built from smaller pieces through mergers and cannibalism, continuing to grow through ongoing accretion. We witness a moment in this process, neither the beginning nor the end, but a particular configuration in the middle of an evolution that stretches from the early universe billions of years into our past to a far future billions of years ahead. And yet, within this vast process, we find ourselves here, now, capable of understanding it. The universe has evolved for 13.8 billion years, following physical laws that produce stars, galaxies, planets, and through processes we still only partially understand: life and consciousness. We are patterns of matter complex enough to contemplate the processes that formed us. We can look at the debris of ancient galactic mergers and recognize them for what they are. We can project forward to future mergers and understand how they'll transform our galaxy. We can situate ourselves within cosmic history, seeing how we fit into the grand narrative of structure formation from the Big Bang to today and beyond. In the end, galactic cannibalism is neither good nor evil, neither beautiful nor ugly. It simply is a fundamental process by which the universe builds complexity from simplicity, large structures from small ones. It operates through gravity, the weakest of the fundamental forces, but the one with infinite range, the one that shapes cosmic structure. It proceeds slowly by human standards, but inexorably. It destroys galaxies as discrete entities while preserving their constituent stars and incorporating them into larger systems. It is creative violence, destructive construction, the universe's way of growing up. We are here, briefly, in this moment between past cannibalism and future consumption, living on a planet orbiting a star that formed from recycled material in a galaxy built through mergers. We're made of atoms, forged in stars that may have belonged to other galaxies. We study the evidence of past mergers, written in stellar streams and chemical abundances. We project forward to future mergers we'll never witness. We inhabit the ruins of smaller galaxies, and those ruins are also foundations, the raw material from which our galaxy constructed itself. If you find this perspective vertiginous, you're not alone. The timescales and spatial scales of cosmic evolution exceed our daily experience so completely that grasping them requires conscious effort. But that effort is worthwhile because it connects us to something larger than ourselves, larger than our planet, larger than our species or our moment in history. We are part of cosmic history, participants in processes that began long before Earth existed and will continue long after our sun dies. Understanding this doesn't diminish us. It enlarges us, reveals how we connect to the furthest reaches of space and time. So tonight, if you look up, remember that some of those stars are immigrants from galaxies that no longer exist. Remember that the Milky Way's band of light represents a structure built through billions of years of cannibalism. Remember that we're falling toward Andromeda, that collision inevitable on timescales measured in billions of years. Remember that everything flows, transforms, becomes. And remember that you are here, now, able to understand these truths, made of matter that has cycled through cosmic history, temporarily configured as a being capable of contemplating its own origins. The universe builds galaxies through cannibalism. It built you through a different process, but one equally dependent on transformation and recycling. You are stardust. Literally, atoms forged in stellar furnaces and dispersed through supernovae. You are also galactic debris, material that may have belonged to multiple different galaxies before ending up in the region of space that became the solar system. You contain within your body the history of cosmic violence, transformed into something capable of wonder. If that thought brings you peace, or awe, or a sense of connection to something vast and ancient, then you've understood what galactic cannibalism teaches us. We are not separate from the universe. We are expressions of it, patterns it takes, temporarily, in one small region, before moving on to other configurations. The cannibalism continues. The mergers continue. The slow, patient violence of gravity continues shaping cosmic structure. And we continue here, watching, understanding, part of it all. Before you go, if this journey through galactic cannibalism has sparked something in you, If you've felt that shift in perspective that comes from seeing yourself as part of cosmic history, consider subscribing to the channel. These explorations into the deepest questions of cosmology and existence take time to research and craft. Your support through a like or subscription helps us continue bringing you these long-form meditations on the universe's most profound mysteries. Together, we're creating a space where complex science meets contemplative wonder, where falling asleep and waking up both become acts of cosmic connection. Thank you for traveling with me through these billions of years, across these millions of light years, into the violent and beautiful processes that built the galaxy we call home. May you look at the stars differently now. May you feel, viscerally, your connection to this ancient process of cosmic construction. And may you rest well, knowing you are part of something vast and ongoing, a small pattern in an immense transformation that stretches from the early universe to a future we can barely imagine. Clear skies and good night.